In this video, we're going to explore measures of variability. So while we are concerned about where the values in our data is actually located, so if I were to just draw, for example, just this graph just representing like almost like a dot plot, we're interested in where the numbers are clustered. But in addition to that, we are also interested in the spread of the data, just how much spread there is from here to here. So measures of location will say where are most of location, where are most of these values, all right? But then what about the spread in the data? And spread, which refers to the variability of the data. And now we're looking at spread, A-D. So spread, as you say, which looks at the variability in the data, is extremely important. If we think about purchasing stocks and investing, then what if the stock price goes from one day $5 to another day $25 to another day $100 back down to $15 and so on? That would be a lot of variability. And what that tells you is that that variability is a measure of risk. That's a fairly risky stock. Most of us wouldn't want to invest in that unless and if we're lucky and we hit the jackpot, we bought it at $15 and then we sold it when it rose to $100. But that is not common, right? So it's going to be a little more difficult to achieve that kind of performance. It's very risky. Chances are you could lose a lot of money. So we want to find ways to measure variability in the data. And so we're going to go for a couple of measures. One is called a range, the interquartile range. So once we find the quartiles, we could calculate this. There's a measure called variance and standard deviation, which is actually related to the variance, and a relative measure called coefficient of variation. So we're going to start off with those, all right? Range is the simplest of them all, which is basically what is the distance between the smallest value and the largest value. And so max minus min, the maximum value minus the minimum, is the range. All right, that's as simple as it gets. And if you want to put a notation, we say x max minus x min. And of course, you could see that this is not always a very reliable measure, because if we have some very extreme values, but most of the values are clustered in the middle. So say, for example, I have a value down here, value up here, but most of my values are around here. Now, if you look at this group, there's not a lot of variability there. But if that is the largest number and the smallest number, then it says, wow, I have this huge range of data. But these are outliers. So it would be nice to be able to get rid of those outliers right here. So by definition, the range is just the max minus the min. The interquartile range. So once we calculate quartiles, now remember we talked about percentiles and quartiles. What we have to learn to do is then calculate the quartiles. So quartile number 1 is the first is 25th percentile. 25th percentile. All right. Quartile number 2 we know is the median, or the same as the 50th percentile. And then Q3 is the 75th percentile. So once we have those, we could get the interquartile range. It is the middle 50% of the data. So to show you what we're talking about here, if I say, let's look at this. And this is our first quarter, Q1. The middle is Q2, and the third quarter is Q3. Then the interquartile range is that middle 50%. So in other words, it is Q3 minus Q1. And that's not hard to calculate at all. So the interquartile range called IQR is simply Q3 minus Q1. All right. And continuing, we're going to introduce you to a measure called variance. Now, we talked about the limitations of the range in that the range is just based on the extreme values. What the interquartile range is attempting to do is to not focus on the extreme values, but rather on the range in the middle of the pack. So that's why we call it interquartile range. We're looking at the range at the middle 50% of the data. And that gives us another measure as well as to what extent we have a fair amount of variability in the data. So we look at the range and also the interquartile range, which can be useful. Now, as we noted that the range and interquartile range does not actually use all the values, wouldn't it be nice if we actually had a measure of variability that used all the values? So let me just show you this on a graph and kind of see what we're looking at here. So what if we had the following? What if we say, okay, if we had a dot plot of all of our values? So we have values right here. We might have a couple of values, maybe one value here, one value. So this is from the lowest value, whatever that is, we're not sure, to the largest value. So we may have 2 values, 3 values. The main thing is this. If we took all of these values, we could calculate an average. The sum of all of the x's divided by n will give us the average of all of these values. If we could locate that sample mean or population mean, either that or it could be a population mean, then what we're now interested in is what is the distance between all these values and that mean. I take a value from here. What is the distance? What is the distance between these values here? So now, when we look at the distance of the values relative to the average. So we are now measuring the variation around the mean, just how far or how distant those values are from the average. And that's another measure of variability. So we fix a point, and that point that we fix is the mean, and then we measure how far we are from that. Now, to do that, we would just need to take the distance for each of those would be xi, the value, minus the mean. And what we can do is that we could say, let us add up all of these values, right? All of these distances, and divide it by the number of distances that we have, which is the sample. And we could say, oh, that will measure variability for us, but there's a problem. What happens is that this value will end up being 0. Why? Because you have positive differences will cancel out the negative differences. So for example, when the value of x is smaller than x bar, you get a negative difference. When it is greater than x bar, you have a positive difference. And so since all of those values were used to calculate the average, when we add and subtract those values from the average, what you will end up finding is that it will sum up to 0. All right. I could prove it mathematically to you, but we don't need to get into the mathematical proof. All right, because all I have to do now is to remove the x bar outside of the bracket, and then what we are left with would be all of the individual values that were in the data set. And what happens is when you add them all up and divide by n, you end up getting x bar anyway. But that x bar will have a positive sign, and if we remove the minus x bar, it's a negative sign. So minus x bar plus positive x bar gives you 0. So the point being is that we cannot use this as a measure of variability. So what do we do then in this case? Well, here's what we do. We say to make sure that we're not being messed up by the negative signs, we will calculate what we call a variance. So we'll calculate a variance. So variance will be the following. We'll say, let's take all of our values, xi, and we will subtract from it the population. And I'm going to start off with population variance. Population variance. We will subtract it, but remember we said if we just added those distances, they will give us 0. So what do? Each case, we square it, and that's how we get rid of the negative signs. So we don't have negatives canceling out positives. We square them, and we add it all up. And then if we divide by the number of values that we have, we call that the variance, all right? And then if we take the square root of that, we call it standard deviation. So the standard deviation would be the square root of xi minus mu squared over n. Okay? So that's called the population standard deviation. Now, what are the symbols that we use for those? We don't have, the symbols that we use for those are as follows. So we would have population variance, symbol is sigma squared. So that's sigma from Greek letter. And so the standard deviation is the square root of sigma squared. The square root of the variance, in that case, is just sigma. And that's the standard deviation, population standard deviation. And that now measures for us variability. It's kind of hard to put it in words, but all we know is that it does give us, the bigger the value is, the more variance there is around the mean. In other words, the numbers are more spread out. Okay, so what happened now if we had a sample instead of the population? How do we do this? If we have a sample instead of the population, then we modify the formula just slightly. So for sample standard deviation, there's an S. Let me just correct that. Sample standard deviation. So when we don't have the population, we denote it by S. S is the square root of xi minus x bar. So that's where the difference comes in. Notice that instead of mu, I now have a sample mean instead of a population mean. And I do exactly the same thing. I square it to make sure that the negative sign doesn't influence it. But instead of dividing by n, we divide by n minus 1. And this is what you call an unbiased estimator. We won't get into the philosophy behind it right now, but this is an unbiased estimator of the population standard deviation. So because this is the sample standard deviation, S is an estimate of sigma. You may recall what I said, that sample values are always estimates of population values. So S estimates sigma for us, all right? And so therefore, if population variance is sigma squared, then sample variance is S squared. S squared. All right? So that's variance. One of these days I'll learn to write properly with this. Okay. So that's cool. Now, I want to give you a variation of the formula that makes it a lot easier for us to do our calculation, because right now, this formula requires a bit of work. So let us actually look at a variation of that formula. Because if we were to use this formula to do our calculations, you'll find yourself doing this. You'll find yourself first finding the mean. We're talking about sample data now. X bar is equal to sum of x divided by n. And then we would have to put a column with our x values, xi, a column with our xi minus x bar, and that's what you notice in your text, and then xi minus x bar squared. And then we have to put all these values down. That's a lot of calculations, but we don't have to. Here's what we calculate. We will actually calculate only 2 columns. That's what we need. It turns out for us that all we will need in this case, let me put it on this side, would be the x values and the x squared values. All the x values, and then when we add them up, we will get the sum of x's and the sum of the x squareds. Now be very, very careful that sum of x squared is not the square of the sum of the x's. Is that we are actually squaring each value separately and then adding them up. So if we had a value over here that was 2, x squared would be 4. 3, x squared would be 9. And then we add those values. Now, it turns out that is what we would use as a formula. So for some population variance, also not population, sample variance, S squared, remember variance is the square, and then when we take the square root, that's when we have the standard deviation, would be given as follows. The sum of the x squareds minus the sum of the x's. And notice I put it in bracket to separate it from this one. All squared over n, the sample size, divided by n minus 1. That is the sample variance. If I had capital N instead of n minus 1, that is population variance. So I could just give you population variance right here. Sigma squared is equal to the sum of the x's squared minus the sum of the x's. I put it in bracket. Notice now I have capital N over capital N, right? Once we have the sample variance or the population variance, then sample standard deviation is just the square root of that. So and I'll just do one of them. S would be the square root of sum of the x squareds, sum of the x's, all squared over n divided by n minus 1. Note that n minus 1 is under the bracket. I mean the square root bracket. In other words, we could put big brackets all around this, all right? That is the formula, shortcut formula that we call it. So it's a shortcut formula, and trust me, it does take less time to use this one than the other one. So that's a shortcut formula. And I just also want to mention to you at this point that the numerator, we have a term for it that I want you to become familiar with as early as possible, called sum of squares. So this numerator right here we call it the sum of squares. So if you think back to the formula that I gave you earlier, let's go back for a second. You see how we have the xi minus x bar and we square it and then we add them up with the sum. So that is the sum of squares and we denote it by SS. And because our variable is labeled x, we call it SSX, the sum of squares due to x. It is this very same numerator that we have here that is equal to this one here on the next page. And so that is SSX. So I want you to become familiar with this because you will see it in our formula table that SSX is equal to the sum of x squared minus the sum of x squared over n. Either n if it's sample or capital N if it's population. So please make a note of that. So that means that I could write in shorthand that standard deviation is, or variance, let's start off with variance. I could write variance S squared is equal to SSX over n minus 1. And standard deviation, S, is equal to the square root of SSX over n minus 1. So please become familiar with that as early as you can. All right? So that is standard deviation. Now, that will measure for us, as I mentioned, the variability of the values around the sample mean or the population mean. So here's the formula that your text gives you, but I gave you a shortcut formula, and this is what it would be if it were population. All right? But we're not going to use this to do our calculations. Standard deviation, as I've already mentioned, is just the square root of the variance. So sample standard deviation, square root of sample variance. Population standard deviation, square root of population variance. Last, I believe this is the last one. One of the things that we want to also be able to measure is what we call relative variation. In other words, can we express the standard deviation as a fraction of the mean? And this has quite a bit of value for us in terms of being able to make sense of the level of variability that we have, particularly if we want to compare two different distributions. If we can say that one of them has a higher coefficient of variation than the other, then that's a way of measuring variability. It's kind of like this. It's kind of if you had two investments, one made $10,000. Let's say two investments. One was a $10,000 investment. The other one was a $50,000 investment. If you're told, oh, my return on the first one was $5,000, my return on the second was $15,000, you're not immediately sure which one was the better investment. But it would make sense if you express the actual amount that you made. So the 5,000 over 10 was a 50% yield. But the 15,000 over 50 was a 30% yield. So while the 15,000 appeared to be more than the 5,000, the reality is that the 5,000 over the 10,000 was a better return on your investment. So that's why it's always good to represent the variability as a fraction of the mean, and that's what we have here. So coefficient of variation is how large the standard deviation is relative to the mean. If it is greater than the mean, so like you have a coefficient of variation of greater than 1, that's a fair amount of variation. So this measure is quite useful. And so coefficient of variation, we call it CV, coefficient So CV is the population over population standard deviation over population mean. That would be for population coefficient of variation, or sample standard deviation over the sample mean. Some people get those confused. Please don't confuse them. If you're dealing with population, everything has to be population. If you're dealing with sample, everything has to be sample. And we usually express that as a percentage, so we multiply it by 100%. So if we say 25% coefficient of variation, then what we mean is that the standard deviation is 25% of the mean. So if the mean is 100, then the standard deviation is 25. All right. That is a very useful measure, and as I said, it's very good for comparing different distributions. So if you want to compare the variation of house prices to cars, so cars to houses, then we collect our data, calculate the mean, standard deviation, and find the coefficient of variation, and then compare them. Do not try to compare the actual values, because houses are in hundreds of thousands of dollars, cars are in tens of thousands of dollars. So they will give you two different measures, and that cannot be directly compared. Okay? So you would have to use a relative measure, and that's where the coefficient of variation is indeed very useful.